we are going for the interrupt. As the name suggests, interrupts are the subroutines which are interrupting the main program. Depending on the priority we are setting, they are going to interrupt the program. So some interrupt, if it is coming and it has been set on high priority, it can stop the running program of this microcontroller. We have to entertain that interrupt and we have then come back to the program. That way the things are happening in case of interrupt. Okay, so it is like its name only, interrupting the main program, but depending on the priority set by us. So those interrupts we are going to check. So very clearly, I'm putting this pin diagram in front of you because I want to show you that INT0 and INT1, actually they are INT0 bar and INT1 bar. These are the interrupts, external interrupts which are there in 8051. Try to understand that 8051 is very basic microcontroller and it is trying to accommodate many of the functionalities. These functionalities are becoming advanced and advanced as we are going for the higher microcontroller. That's why if all the functionality at this lower level, if we are understanding in detail, it will be easy for us to understand the complex functionality of the higher microcontrollers or processors. Is it right? So what functionality I'm talking about here? I'm talking about interrupt functionality. And these two pins, they are taking the external interrupt. Yes, I'm on first slide only. I'm on the pin diagram only. Oh. Now, is it moving? Okay. Achha, now it is there, but I am out of, okay. Now is the PPT changing? Third slide. Okay, I will stop sharing and again because what is happening when I'm coming out of the presentation mode, it is visible. One minute. Check in presentation mode. Is it slide 4? 5? Okay. Actually, it is in presentation mode. Now I came out of presentation mode. Tell me one thing. Properly, the slide is visible here. I'll keep out of the presentation mode. Okay. Okay, I'll keep like this one. Okay, sorry for the disturbance. So, two interrupt pin, INT0 and INT1, they are what entertaining the external interrupt. Now, we'll at first try to understand why we need this interrupt. Check that in 8051, if we are using the 8051 for some application, let it be that application is of washing machine. I actually, as a lady, as I always used to give that example, so that is the washing machine. I'm using this 8051 for programming the washing machine. For that I'm using this microcontroller. Okay, and the door, it's close or open, that signal is coming from, let it be INT0, and the second water tap is on or not, that is coming from INT1. So what are the two interrupt I'm checking for my washing machine? One is about the door and other one is about the water tap. Is it flowing or not? Water is there or not? And try to understand that both the things are very important. So what can happen? What will happen in starting? I am putting the cloth in washing machine, putting the detergent in the tray, and then I start the button. I set the program and I start the button. But now what is happening? Program will not start running. Why? Because at first it will check the interrupt. Which interrupt? Door interrupt. And as door is not closed, there only error will come out to be there, right? So which one is the priority interrupt? Door is closed or not, that is the priority. Who is going on the second priority? Second priority, obviously, if door is closed, it will check for the water, right? That is the second priority. So that way interrupts are there. That way we need external interrupts, right? And they are playing very important role in our program. So do you understand? These are the interrupts. More the interrupt, more external things we can check for. Okay, now we'll check what different interrupts are there in 8051. But before that, we'll check, as I am telling you, when my main program is running, okay, this program is smoothly running without the interrupt. But if I have the interrupt 1, 2, and 3, these interrupts are there. So what my main program is doing, chunk of the program is running, it is coming to interrupt subroutine, executing that interrupt subroutine. Once it is over, once the written is the instruction coming out to be there at the end, it is coming back to the main program. Again, the second chunk of the program will get executed. Again, it will check for the interrupt if it has been asked for the interrupt. That way, my main program, which was going smoothly, due to the presence of interrupt, it has to entertain those interrupts because they are having the priority in my program. So these are the interrupts. Last time we have in short gone through it, so I'll go bit fast and we'll go for the details of interrupt. So interrupt is an external or internal event. I explained you about the external events, right, by showing you int0 and int1. But few interrupts are internal also, means internally in the programming we can use the timer as an interrupt. Some other internal interrupts are also there. Serial communication can act as the interrupt. So interrupt not only external, they can be internal also. Okay, so interrupt versus polling. A single microcontroller can serve several devices. There are two ways to do that. What? One is interrupt, other one is polling. Okay, the program which is associated with interrupt is called as interrupt service routine. We have seen last time. What? ISR. In the main program, when the main program is running, for some time, if interrupt is coming, it has to go for what? Interrupt service routine. What polling is doing? It is deciding the priority of the interrupt. That is polling, as the name suggests. Okay, so ISRs are there or interrupt handlers are there. Now, step in executing an interrupt. So what interrupt will do? It will finish current instruction and save the program counter on stack. What is program counter? The instruction which we are executing at present, that is in program counter. Okay, so what will happen? When the interrupt is coming, at first, whatever is the instruction in hand, that will be executed. And after that, the next part of the program will be saved in stack. And where the program will jump? It will jump to first location in memory, depends on type of interrupt. Now look, interrupt means what? It is a chunk, a part of the program. So obviously it needs some memory. So some 8 locations has been given to the interrupt in the memory for one interrupt. For the second interrupt, again 8 locations are given, and so on. For obviously there are 5 interrupts in 8051. So for them 888, that way the locations are given and particular memory address is given for saving those those instructions. So what will happen? The present instruction will be completed. The next part will be saved to what? Stack of the regular program, and it will jump to what? It will jump to the interrupt. Okay, it will execute that interrupt, start to execute the interrupt service routine, that is ISR. And what is at last of ISR? RETI, return is there, return interrupt. So or return from interrupt. So what is the last instruction there? RETI, return from interrupt. So it will come back, whatever is there on the stack, it will be taken and start executing it. Upon executing RETI, the microcontroller returned to the place where it was interrupted. Where it was interrupted? Something was there in the PC which was saved on the stack. So again, the main program will start executing. Okay, so this part where we are pushing the program counter on stack, it is called as push instruction. And when we are recovering PC from stack, it is called as what? Pop instruction. So two instructions are there, push and pop. Do you got it? One is push instruction when we are pushing the PC program counter on stack. And what is pop? We are recovering our PC from stack so that that instruction will run and the program will continue. So this is how interrupt subroutine is executed. Okay, then after that, so look here, whatever we have seen in the theory, this diagram is trying to tell us main program, instruction n plus 1, n plus 2. That way the instructions are getting executed. Here, look here, where after n plus 1 interrupt occurred. Okay, so what will happen? After this is happening, this n plus 2, we are saving it on what? Stack. Save PSW, program status word, save return address, set PC to vector address. Okay, we are saving to what? To the stack. And interrupt service routine is executed. After interrupt service routine, what we are doing, or let it be, this is the interrupt service routine. What instruction? M plus 1, M plus 2, M plus 2 plus M, and interrupt return from interrupt. What is the last instruction? We are returning back from interrupt. So it is getting executed. What will happen after that? We will restore our PSW. Whatever was saved in PSW, will restore it. Set PC to return address, and again we will start running the program. That way the thing is happening while executing the interrupt. Okay, now what different sources of interrupts are there in 8051? So as I told you, two external sources are there. Other than two external sources, one reset is acting as the interrupt for 8051. Okay. Second is timer 0 overflow. Means which flag? Do you remember? There is TF0 flag and TF1 flag. We can use them as the interrupt for stopping some or halting for some time, halting some program. What? TF0 and TF1. The the timer flags which are there, they can act as the interrupt. Okay. So for example, I am setting some, what example I can give here is in timer, I am setting some time. Okay. And what I want is that let it be a oven is there and I kept it on preheating mode, and after some time, the timer which has been set, after that it has to go to the, or it has to stop. Okay. So here what I am doing, I am setting the timer and I am using that timer as interrupt. What it will interrupt? Power supply it will interrupt, and the oven will stop working after that much time. So that way, or for any application you can think of, internally you can set the delay timing, and after that timing, flag will set and flag will stop the program for a while, and then the remaining part will get executed. So timer 0 overflow, timer 1 overflow, they are also acting as the interrupt. Okay, so reset, two timer and two external interrupt, and last one is what? Serial port event. We know that 8051 has serial port. So if some event is happening on it, some signal is coming on it, that can act as interrupt. And what type of event? It's buffer. We are going to check it's buffered next time. We are going for that serial communication. Buffer empty, buffer full. This can act as the interrupt. So that way 1, 2, 3, 4, 5, 6. 6 interrupts are available in 8051, such a small microcontroller. These many interrupts are available. Okay. Now coming next, as I told you, each interrupt has its own subroutine. Okay. Means when that interrupt is setting, we are going to a particular memory location, and what has been told on that memory location, we have to do it. So your external interrupt 0. At what memory location it is going? 003H. At this memory location it has to go. Okay. Timer 0 overflow. I told you this flag will set. And it will take to which memory location? 000BH. Okay. Then external interrupt 1, where it will take 0013H. That way, these are the memory location where it has been taken. Try to understand between 3 and B, B and 13, 13 and 1B. 8 memory locations are available. Vector of what? 8. That much routine has to be written there, which will be executed, and your program will return back to the main program. Okay. So what is interrupting? And then after interruption, what has to be done? Where it is written? At these location it has been written. Okay. So these things are interrupting your main program, and after interrupting, it has to go to the particular location. What has been written on those those location, it has to be executed, then to come back to the main program. That way the thing is happening. Okay, so try to understand the importance of these memory location. Try to understand that there are only 8 memory location between these vector. This is called as vector. 3 to A, B to 12, 13 to 1A, 1B to 22, and 23 to further 8 locations will be used. So that way, that much area has been given for writing down the ISR, interrupt subroutine. Okay, now we will check the priority of this interrupt. I'll go for the priority of interrupt. But before going to the priority of interrupt, we are checking one register, interrupt enable register. Now, not necessary that I want interrupt in my program. If I don't want any interrupt in my program, I will set all 0 in this interrupt enable register. In that case, whatever will happen on the external pin, whatever happened to the timer, it will not be taken care of. If my program is that plain, I don't want it to be interrupted by anything. In that case, what I have to do? I have to disable all these bits. Do you understood it? Interrupt enable register. This is helping to enable the register. Now, if I want all the interrupt to be taken care of, some program is there in which I want 2 external interrupt to be taken care of, timer also to be taken care of, both the timer to be taken care of, serial communication to be taken care of. In that case, I will put EA to be 1. Look what this bit, MSB, EA, which is IE7, interrupt enable 7th bit, 0 to 7. That's why I'm calling it as 7. Disable all interrupt if it is 0. And if it is 1, then what it is doing? It is enabling all the interrupts. Okay. So, just a minute. Okay, some noise was there. Sorry. Okay. So, EA, if equals to 1, all the interrupt, what? Serial interrupt, timer interrupt, external interrupt, second timer, second external, everything will get enabled just by putting this 1. Now, I don't want all the interrupts. Some of the interrupt I want to be active. In that case, what will happen? I will put this EA to be 0, and those particular interrupt bit, I have to make them 1. Okay. Now, before coming to that, EA we have done these 2 bits. These 2 bits, they are not implemented. They are reserved for future use. After that, ES. Why this happened? Because we have only how many? 6 interrupts. Out of it, reset is the button. So we don't need it in this IE. It is the compulsory interrupt to be there. We don't need it in enable register. Okay. So how many are remaining? 5 are remaining. And what is the 6th? All together. That is the 6th. Okay. That's why these 2 are kept for future use. After that, EA4, ES. What ES suggests? Serial interrupt. right? Enable or disable serial port interrupt. Is your serial buffer full? Is your serial buffer empty? If that is the interrupt you want to be taken care of, you have to make ES 1. Okay, else you have to keep ES 0. ET1 means timer 1. Enable timer 1 interrupt. Okay, what is that ET1? If flag of timer is set, what is that flag? Do you remember the flag of timer? If it is 1, overflow flag of timer is 1. And that one flag you have to use at the interrupt. If you want it to use as the interrupt, you have to set this bit as 1. Similarly, on the external interrupt pin 1, if there is any signal you want it as an interrupt, put this to be 1. For timer 0, for external pin 0, you have to make this or this 1. For example, I have to set serial and I have to set timer 1. So I'll be setting these two as 1 and remaining I'll keep 0. That way can happen. So it depends which interrupt you are using. So very important register, which is interrupt enable register, we have to use in our program depending on our requirement. Okay, now mm, look here, they have given the example set b. This is the bit addressable register. How is this register? Bit addressable. You can play with the single bit in the program. You can write the single bit like this. Look what this instruction is saying. Set b ea means it is setting. Setting means writing value 1, where in the bit, which bit? As it is b, it is bit ea. Okay, so in the register IE, this EA become 1 due to this instruction. Are you getting? Set B IE dot 7. What we are setting? First bit we are setting 1. Remaining bit will be 0. This instruction is the obviously not the C instruction, but it is the which language I told you? Assembly language instruction, but I'm trying to tell here what is happening. We can play with the single bit. Set B ET0. Okay, I'll go to the register. Which one? ET0. This only one bit will be set as 1, remaining as 0. And if you want to write down the instruction for complete register, instead of writing B, you can write it for the complete register. How? Like this. Look at this instruction. Move IE. What value we are moving in IE? Hash 1 0 0 1 0 1 1 0 means EA we are making 1. Then next two, they are of no use, we are making them 0. Then the next is 1 0 1 1 0. You can think like here 1 0 0 1 1 0, something like that. So whatever are the bit, they are setting the complete register. So either you can go for setting the single bit, or you can think of setting the complete register. That is what called as the bit addressable. Okay, now look here, this is just kept in front of you to think you how the interrupt can be used. Now look, what is the program? Write a program to generate two square waves. Two square wave we are generating. One is of 5 kilohertz and other one is of 25 kilohertz. One is generated at pin 1.3, other is generated at pin 2.3. Okay, so obviously we will generate it using timer. Okay, what will be generating it? Using the timer. We know very well how to generate it using timer. We have seen that type of the diagram. But what I'm trying to tell you here is we are using the interrupt. Which interrupts? Internal interrupt. Timer interrupt. Okay, as we are generating two square wave, you have to use timer 0 as well as timer 1. And those timer, they have to what? Its overflow flag will be turning on after 100 microsecond in this case, and in this case after 20 microsecond. Are you getting? For getting the square wave, it has to remain on for 100 microsecond. It has to go down, remain on for other 100 microsecond. So it has to change its position after 100 microseconds. So who will tell it? Timer will tell it. For example, timer 0 is used here. Its overflow flag, we will write down the delay of 100 microseconds in that timer. After 100 microseconds, the timer flag will be set. And once it is set, we are getting the interrupt. And that interrupt will change this pin from 1 to 0. Are you getting? Here is how we are using the interrupt. What is happening here? In this case, the delay required is 20 microsecond because my frequency is of 25 kilohertz. 25 kilohertz frequency means 1 by 25 kilohertz will give you 40 microsecond. So complete cycle is of 40 microsecond, on time 20, off time 20. So what do you want? 20 microsecond signal has to remain high. After that, it has to go down, remain low, right? And so on and so on. So you have to generate the interrupt after every 20 microsecond. Who is generating the interrupt? Flag of the timer is generating. Which timer we are using here? Timer 1. Its flag will give us the interrupt and we will change to low, from high to low, low to high, and so on. We are generating the frequency. This is how we are using two internal timer. Do you got it? I want you people even to take it down and try the program in C for this. You will get the idea what we are using here. Okay, so I'll not go for the calculation. We have seen it last time, and what to feed there, how to get the delay, how to generate the square wave. But just I would like to tell you what we are using. TF1 flag. This flag we are using. We are checking for this flag. When this flag is 0, when it is turning to 1, at that time wave 2 become inverse of wave 2. We are changing the position 1 to 0, 0 to 1. That is happening. Okay, so think about these interrupt. I will not go for much for that program. Okay, now after this, external interrupt type we have to talk about. Okay, we have talked about the internal interrupt of the timer. Now we have to talk about the external interrupt type control. So IE0 or IE1, these two bit of your IE register. Okay, that interrupt enable register, EA register, interrupt enable register, there were two pin. What? IE0, IE1, two bits were there, external interrupt 0. Okay, so these are set by CPU when external interrupt age high to low is detected. Look here, I'll just once go back and show you where is this IE0 or IE1. IE0 and IE1. Oh, sorry. External interrupt. Now IE0 is there and IE2 is there, not IE1. They have written it as IE1. 1 minute. In TCON register. Sorry. In case of timer control register, TCON registers. Yes, coming here. This one. Do you remember we have used this register in the timer? This upper 4 bits, timer 0 and timer 1, we have used for setting the timer, and lower 4 bit we have not talked about. And now for external interrupt type control, we are talking about this lower 4 bit. And look here, what is it? IE1, IT1, IE0 and IT0. And they are for what? For interrupt. Okay, so now today we have to talk about these 4 bits. So what is this? I0, external interrupt age flag. Okay, when it is setting, these are all the flags. Is it right? These are all the flag in TCON. These flags were setting due to timer, and these flags were setting due to what? Interrupt. So if the external interrupt 0 or 1 age flag, when it is setting, this one, IE0 or IE1, these two flags, they are setting, they are set by CPU when external interrupt age high to low is detected. Where the external interrupt is coming, two pins are there, INT 0 and INT 1. I have shown you in the pin diagram. On that pin, if some high to low transition is happening, at that time, if it is happening on the pin INT 0, IE0 flag will be set. If it is happening on INT 1, IE1 flag will be set 1. Are you getting? Can you relate? This does not affect high to low while ISR is executed. Okay, it is not, and this flag is setting, but if it does not affected by high to low while ISR is executed. Okay, so once in starting it will check and let the ISR be executed. After that, it is cleared by CPU when RETI executed. Try to understand what is happening. Interrupt is coming. Once the interrupt is coming, who will set? These flag will set. They will remain in the same position till the ISR routine is completed. Once it is completed, they will be cleared or resetted. And when that ISR is completing, this is the last instruction, RETI. At this end, ISR is completing. ISR means what? Interrupt subroutine. They are completing. So it is completed. Obviously, the flag has to be clear. Why it has to be clear? So that again, if any interrupt is coming, it has to engage with that interrupt or it has to entertain that interrupt. So does not latch low level triggered interrupt. Okay, so this has to be kept in mind. You have to keep in mind that there is one register TCON which was having 4-bit of timer, but lower 4-bit they are for interrupt, and we can utilize this flag in the program, and on basis of this flag we can decide the interrupt is there, ISR is completed or not. Okay, now we'll talk about IT0 or IT1, remaining 2-bit IT1, IT0. So interrupt 0 or 1 type control bit. These are control bits. Okay. And so as they are control, who is controlling it? By writing the program, we are controlling it. It is for setting or cleared by software. We can set it by program. We can set it or we can clear it. Now look, if I am setting IT to be equals to 1, this IT, if it is 1, what will happen to the interrupt? How will check for the interrupt? It will be age triggered. Okay. And if IT is 0, it is low level triggered. Two things are there. One is age trigger, other one is level trigger. Age means for high to low going transition, that is called as age trigger. And after that, when the signal become constant, it is level triggered. So IT1 and IT0, sorry, IT equals to 1 or IT equals to 0 will either go for age triggering. This we are saying high to low going means what? Age triggering. And 0, it will go for level trigger. That way the control is there for the external interrupt. Okay, so very clearly in T control, T con, the lower 4-bit, they are for interrupt, and those are the flag. IT1 and IT0 can be set in the program for age and level trigger, and IE0 and I1 can be utilized for checking if interrupt occurred or not. Okay, so that was the thing. These are the just diagrams of age triggered and level triggered. Look, now the timer which we talked about, the 2 square wave generation using timer we talked about, there which interrupt we use? Timer interrupt was utilized. Now here in the example which is coming, we are utilizing external interrupt. I'll keep that diagram in front of you, you will understand. Look what is it? Switch 1, switch 2. Where they are connected to interrupt 0 and interrupt 1, means pin 3.2, pin 3.3. What are there? Two switches are there. If this switch is on, then we have to turn on these LEDs. If this switch is on, we have to turn on these LEDs. We'll check what is the statement. Two switches are connected to pin 3.2 and 3.3. When switch is pressed, the corresponding line goes low, writing program 2. We'll check what will happen. Light all LEDs connected to port 0 if first switch is pressed. Light all LEDs connected to port 2 if second switch is pressed. Do you got the statement as well as diagram very clearly? Pressing this switch to the port P0, all the 8 LEDs which are connected, they have to glow. Okay, when this switch is pressed, we have to glow the LED. So what we are taking care of, these are the external interrupt. We are using those. We are taking care of these external interrupt in our program for turning on these LEDs, right? That has to be done. Now, obviously, I'll not go to the program, but just would like to tell you what care has to be taken of, which register we have to take care of. T control register. Look, this register, this part we have to take care of, right? Why? Because IE1, IE0, let it be IE0 or IE1, these are external interrupt, and obviously the switches are connected to the external interrupt. And light, we are turning on the light, means what? We are we are closing the switch, we are pressing the switch. This switch is pressed, means what signal is going here? High signal is going here. If you know int bar is there, this is going to be high, means internally inside what is going? Low is going inside because it is int bar. Okay, so high to low transition is going inside, and once high to low transition is going inside, what will happen when high to low transition is detected? That interrupt, maybe I1 or I0, will be set. So this will be set, means ISR will be executed. What will executed? Where it will go? It will go that there is the interrupt subroutine. That subroutine will be executed. What is that subroutine we need here? In our case, that subroutine is to turn on these LEDs. That program will turn on the LED. Are you getting? Similar thing will happen with the lower one. Again, try to understand this example. Try to write down the program of this example using TCON register, lower 4-bit of TCON register. In short, I will try to show you here enable register. No, it has been written by different way, but TCON register can be used there to do it. Which instruction? IE instruction. IE instruction. Using it, we can do it. Okay. And the last one is serial interrupt. What is remaining is serial interrupt. Particularly, I am not putting those program in front of you because what is the thing? Writing the program is our own way. Okay. You will get the program everywhere or anywhere. If you are putting that statement, you are going to get the program, but everyone has its own way to write down the program. That's why I'm not putting on trying to explain every step of program to you. What is important? To utilize every interrupt. So go for any program, try utilizing them. Okay. Now the next statement which I am putting here is about serial interrupt. Utilizing the serial interrupt. As I told you, there is one serial communication in case of 8051. So that we are utilizing here. Obviously, after this, we are going for the serial communication. So some part, whatever is possible to show you here, I'll show, and then we'll go for the serial communication. So you have to write a program which read data from P1 and write it to P2 continuously while giving a copy of it to serial COM port to be transferred serially. Okay, so there is one port P1, there is other port P2. So we are reading the data from port P1. Port P1 is acting as an input port, and writing same data as port P2. Means P2 is acting as the output port. Continuously the thing is happening, and copy of it. What we are doing to the serial COM port, we are copying it to the serial COM port to be transferred serially also. Okay, so it is going to serial communication and bit by bit it is getting transferred. Whereas P1 and P2, how they are? They are the parallel port. Okay, parallel it is happening, and here in serial way it is happening. And for this, we are assuming the frequency of 8051 to be 11.0592 megahertz and baud rate of 9600. So this way, the serial interrupt can be used. Okay. So that is the program. Now, the thing is utilizing or telling about that program. Just I gave you the statement. If you are noting down, please note down that statement, what is happening here. And while understanding the serial communication, we'll go for it. Or some type of this type of program will do there. Just try to understand what is happening in this program. In detail, we'll not go here. In the serial communication, we'll talk about it because presently you don't know the SFRs, special function registers of serial communication. So it will be confusing for you. That's why just the statement is present here in front of you. Okay, I will go to the next slide. That is interrupt priority. We are talking about the priority of the interrupt. Okay, we have seen enabling the interrupt, but if all interrupts are enabled, which will be served at first? If at a time they are coming, which will be served at first? That has to be checked, and that is called as what? Interrupt priority. So, what if two interrupt sources interrupt at same time? Obviously, some priority has to be set, right? I told you that in case of oven or washing machine, if door is not closed, so that is the most prior thing to be done at first, other than any other interrupt, right? So priority has to be decided. The interrupt with the highest priority get serviced first. All interrupt have a power on default priority order. Okay, once you are turning on power on default priority, once I'm turning on my microcontroller, what priority is given? This type of priority. Without setting, I can set my priority, but if we are not setting the priority, in that case, by default, what is the priority? External interrupt 0 will be served at first. Timer interrupt 0 on the second number, external interrupt 1 on the third number, timer interrupt 1 on the fourth number, and serial communication on the fifth number. This way it is done. And the sixth one is reset. That switch is there on the microcontroller, that is in our hand to reset it. Okay, so that way the priority is there. So depending on my application, my priority in the application, I will be connecting those inputs accordingly. Is it right? I'll be connecting. The thing which has to be taken care at first will be connected to external interrupt 0, right? The thing which can be served on the second time, some delay which can be served on the second time, can be given to interrupt 0 and so on. So this is what default priority. Priority can also be set to high or low by IP register. That is the next thing. This is default, and we are going for next IP register, interrupt priority register. Here we can set the priority, and I think you understood it. First two bits are reserved. What about this PT2? By this name, what do you understand? It is the timer PT2, no? T2. Timer to interrupt. Priority bit. And actually, timer 2 is in 8052, not in 51. So for again 51, this is free bit. In 52, there is timer 0, timer 1, timer 2. So this is PT2 interrupt. PS, this is for serial communication. Means if I am making this bit 1 and other bit 0, this will be the highest priority bit. What about the next priority? It will come to the default priority, and in that, external will be now on second, timer on third, external interrupt 1 on fourth, and so on. So what I did is I set 1 here, remaining I have not given. That's why PS will be served on the most prior basis. Remaining, again it will go to the default, and accordingly it will set. I think you got it for the remaining. So depending on what we are setting, accordingly it will serve for the priority. I'll come out of it. Here is one example given. move IP. What we are setting in this IP register, we are setting 00000. How many? 50. Then 100B. Bitwise we are setting. H we have not written. We can write down H also. In that case, we have to give hexadecimal. Here we are writing bitwise. So 000, 0 and 0. 50 are there. This is 100. So px1 means px1, that is this interrupt is at highest priority. Who is so int1? What is px1? External interrupt 1, which has been shown by what? int1. It is on highest priority. And what about the other priorities? It will be decided by the default priority and so on. I'll come out of it. You understood it. So that way interrupts are there. Now I'm going to serial communication. Today I want to complete with 8051. So I'll go fast to the serial communication. I will stop sharing this and we'll go there. These slides are visible to you? Okay. So serial communication. This functionality of 8051, one important functionality is about the serial communication. Generally, when long distance communication is expected, at that time we are going for serial communication. Okay, and thus in case of 8051, there is pin RxD and TXD. Okay, these two pins are related with serial communication. Okay, so using this pin, we can think of communicating from microcontroller to that serial port or from the serial port to the microcontroller. Okay, so that is serial communication. So basic of serial communication, I'll not put much time in it. Same, obviously, it can be parallel is expensive because many wires are required. Then it will be short distance. Though it is fast, it is short distance. Whereas serial communication, which is cheaper, two different cities by modem can be connected and so on. So this is how on the single wire the communication is happening. Whereas in case of parallel, this way number of wires are required to communicate. Okay. Now, when we say the method of serial communication, it can be simplex type, that is simply transmitter to receiver. It can be half duplex, means transmitter to receiver, or on the other side means on the on the sending side there is transmitter as well as receiver. Similarly, on the receiving side again both things are there, and thus single bandwidth has been used in half duplex mode, or there can be full duplex. Arrow has to be there on this side. There is transmission and receiver on both the sides. Okay, we are not much interested in it, so we are talking about the serial communication. It has again two ways. One is synchronous and other one is asynchronous. What we mean by synchronous, it transfer a block of data at a particular time. In synchronization with clock, that communication is happening. Okay. And what about asynchronous? It transfer a single byte at a time. So special IC chip made by manufacturer. It is USART, Universal Synchronous Asynchronous Receiver Transmitter. And other one is Universal Asynchronous Receiver Transmitter. So these two things are there. USART is there and UART is there. Okay. This is Universal Synchronous Asynchronous Receiver Transmitter, and this is what? Universal Asynchronous Receiver Transmitter. And I gave you the meaning of synchronous and asynchronous. Now just keep in mind that whenever we are sending the data in series one by one, when we are sending the 1 and 0, we have to put them in frame. Right? We must know what is the starting data, what is the ending data. We must send it in frame. So data coming in at the receiver end of data line in serial data transfer is all ones and zero. It is difficult to make sense of data unless the sender and receiver agree on set of rules. Is it right? They have to make one frame and in starting of frame and at the end of frame they have to decide sending some bits according to the protocol which is known to the sender as well as the receiver. Then only they can unpack it and understand it, else they may confuse that data. They may confuse what is from the first frame and what is the other frame. Okay, so that is called as what? Protocol. On how the data is packed, how many bits constitute a character, and when the data begins and ends. Is it right? So that is important part of the serial communication, and that's why when the framing is happening, in the start of framing there has to be start bit. Okay, and at the end of the frame there has to be stop bit. Okay, and in between what is there? Frame is there. How is this frame? It is 1, these many zeros, and then 1 and 0. That way D0 to D7 is my frame. It has started by 0, which is called a start bit. It is ended by 1, which is stop bit. So that way the communication has to happen. Every frame has to be covered by start and stop bit. When there is no transfer, the signal is okay. I'll just go through it. In synchronous method, data is placed between start and stop bit, which is called as framing. Right? When there is no transfer, the signal is high transmission. Begin with low bit, then 8-bit data. In that 8-bit data, LSB is first. Finally, 1. That is the stop bit. That is how it is happening. Now, this data transfer rate is called as baud rate. That is again one more important thing. While communicating with the computer, I think some noise is there. I will mute it. One. So please mute on your side. Some noise is there. Okay, so that way frame is there. Now this frame, okay, actually this frame where I am saying 1, 5, 0, then 1, 0. This is in ASCII code, it is A. What is it? A. Look, it is 1, 0, 0. Sorry, this is LSB. Na? So in total it is 0. This is MSB. 0, 1, 0, 0. Means how much? Collecting these 4 together, it is 4. Collecting these 4 bit together. And then there is 0, 0, 0, 1. Means how much? 1. So actually in hexadecimal it is 41. How much it is? 41. And in ASCII, how much it is? 8. Means when you are sending this frame, what you are sending? You are sending the letter A in ASCII. Okay, so that is what we are sending. Now, this data transfer is happening in bits per second. The rate of data transfer in serial communication is happening what? Bits per second. And another widely used terminology is baud rate. Okay, and what is that baud rate? This baud rate is number of signal changes per second. In every second, how much 0 to 1 and 1 to 0 transitions are happening in your signal, that is baud rate. Okay, I'll go here. For example, consider this total thing. Consider this total thing. This is consider it to be 1, 0, 1. All is 0, again 1, 0, and 1. Let it be. These many bits are getting transmitted in 1 second. Tell me its baud rate. So we'll check for the baud rate. 1 to 0 transition. There is 1 transition. 0 to 1 transition. 2, 1 to 0 transition. 3, 0 to 1 transition. 4, 1 to 0 transition. 5, 0 to 1 transition. 6, and 1 to 0 transition. 7. So what is baud rate of this? 7 is the baud rate for this. Do you understand? How many changes, transition from 0 to 1 and 1 to 0 are happening? That is baud rate. What is bit rate? Bit rate is different. If I say this is happening in 1 second, what is the bit rate in this case? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 is the bit rate. So obviously baud rate is generally lower than the bit rate. So that is one more terminology. Try to understand this terminology. What? Bit per second and baud rate. Okay. Generally, this communication, serial communication, is measured in terms of what? Baud rate. So single change of signal, sometime, yes. Any problem? Okay. So single change of signal is giving, single change of signal sometimes transfer several bits of data. Uh, Hello. So please keep yourself on mute. Okay. So data transfer rate, that is baud rate. Now, when we are coming to the serial communication, one more important thing we have to take care of is RS-232 standard. Okay, it is the most widely used serial IO interfacing standard. What is happening? We are interfacing our microcontroller, which talk in terms of 0 and 1, which is 5 volt and 0 volt, and it has to interface with this serial communication port, which has some different requirement of voltage. Okay, that's why this RS-232 standard, it has to, we have to talk about, or we have to understand. So most widely used serial IO interface standard is what? RS-232. This standard set long before transistor logic family. So it's very old, and now also it has been used. And look, what is it? The input and output voltage levels are not compatible with TTL. Okay, so they are not compatible with our 805. In RS-232, logic 1 is represented by what? In this range, anything can be there, -3 to -25 volt. Okay, and logic 0 +3 to +25 volt. What I told you, 8051 is talking in terms of 0 and 5 volt. 0 is low, 5 is high. Whereas in this case, logic 1 means high is in this range, -3 to -25, and logic 0 is from +3 to +25. So what is required? Some matching is required between that port, serial port, and the microcontroller. And who is there? Voltage converter. MAX232 is the voltage converter, which is acting between the 8051, which is working on which logic? TTL logic, that is transistor logic, and RS-232. Okay, so who is making the compatible arrangement? MAX232. So I'll go there for MAX232 and show you the diagram. So look, something like this. This is your 8051, which TTL logic, which is the logic it is working on? TTL logic. P3.1 is your serial transmitter. P3.0, this pin is your serial receiver. Read or transmit, right? Who is in between? MAX232. And then we are connecting it to what? Serial port. Look, this is the diagram of serial port. Is it right? Of your computer, of your laptop. This type of serial port is there. Okay. So to be compatible with this, we need this MAX232 in between, so that whatever it is understood by this one, and whatever 0 we are sending, it will be understood by this, and same thing will happen when the signal is coming back. Okay, no need to go in detail of this, just we must know that whenever we have to interface 8051 and the serial port, we need what? MAX232 in between. Now the other thing, how will be the communication between 8051 to PC? To our PC, we are connecting 8051. At first, what we have to do? Connect TXD to RXD and RXD to TXD from PC to 8051. Like this in this diagram. Is it right? This TXD has to be connected to the RXD of PC, and this RXD has to be connected to the TXD of the PC. Is it right? Signal will go, signal will come. That way. Use MAX232 to transform signal from TTL to RS232. Obviously, in between what is there? MAX232 is there. Now the next thing, the baud rate of 8051 must match the baud rate of PC. What you have to do is, you have to set the baud rate of your 8051 so that the rate with which you are sending the signal, it must match with the rate of PC. And what are those standard baud rate? 2400, 4800, 9600, 19200, 38400. Okay. Generally, we are doing the communication with 9600 as the baud rate. Okay. And I told you the definition of baud rate. Which mode we are using? We are using serial mode 1. Which timer we are using? Timer 1 is used. 8051 UART divide. Now further, what is happening? Try to understand. Why we are using the timer? The reason for using the timer is for setting this baud rate. Okay, we have to set this baud rate. Now 8051 UART divides the machine cycle by 32. So how is the machine cycle?
Recording stopped.
How is the machine cycle already?
Recording in progress.
Machine cycle is already the clock frequency divided by 12. UART is further dividing it by 32. But then also we are not getting this baud rate, so timer will be required so that again the division will happen. Now, machine cycle, which is 1 by 12 external frequency, that is happening. We use timer 1. As we have seen here, we are using timer 1, but in which mode? Auto reload mode, that is mode 2. So all these things are required to be set in program. Okay. Done. So look here, this diagram is trying to explain 8051 transfer and receive data serially at many different baud rates. The baud rate in 8051 is programmable. So from that side we are programming. This is done with help of timer 1. Look how my crystal oscillator getting divided by 12. Okay, giving what? Machine cycle. UART, again it is dividing that by 32. And then to get the exact baud rate, we are using timer. Okay, so timer, it generates the delay or it reduces the frequency, right? So it will take us to the particular baud rate. Is this readable? This is one example which is trying to tell how to set the baud rate. Okay, or it is, okay, I'll tell you. Now look, as we are saying, we are using timer 1. And in which mode we are using timer 1 for setting the baud rate? In mode 2 we are using the timer to set the baud rate. So look what to be done in that timer. Timer 1, it's as we are using it in mode 2. Mode 2 means auto reload mode of the timer. Okay, so only 8 bits are used, remaining 8 bits are used to reload it. Okay, so TH1 has been used, higher 8 bits have, only 4 bits are used. It is the 8-bit timer, 4 bits are used. In decimal it is 3, okay, minus 3, 8 bits are used. Sorry. So baud rate, when you have to set the baud rate 9600 in decimal, in TH1, what is required to be there? Minus 3. And minus 3 in hex is FD. So if you have to set the baud rate of serial communication to be 9600, what is required to be done there? Timer has to be configured in mode 2, and there in TH1, what you have to load? You have to load FD. What do you understand by FD? FD means minus 3. If you have to set the baud rate to 4800, you have to load FA. What do you mean by FA? Minus 6. If you want it to be 2400, F4 has to be loaded. So for this standard frequency, these are the value to be loaded in the timer, and you have to keep that timer in mode 2 so that auto reload will happen. Again and again it will get loaded after every cycle, and you get the required standard baud rate. Okay, so this is the thing to be done. Now about the serial communication. Now look what is happening. This is your 8051 internal bus. This whatever data is there on the internal bus, serially we have to transfer it. So it will come here in S buffer. This is the buffer register. Here the data will come. Okay. Here as a clock to this serial bus, what is there? Baud rate clock is there. With that baud rate, one by one that bit will be pushed on the pin TXD and will be taken outside, right? So that way the data is going out. Now, some data is externally coming here. So it will come here to this D. This is the shift register made up of D flip-flop. Its clock. Who is the clock? Baud rate is the clock. That data one by one bit, it will get shifted and then it will come to your S buffer. From the S buffer, it will come inside. Keep in mind that while going out, it will be put between the start and stop bit. That particular frame will be put. While coming inside, it will be removed from the start and stop bit and it will come to your microcontroller. That is how the serial port is working. Okay, so what register I introduced here is SBUF. SBUF is a 8-bit register used solely for serial communication, right? A byte of data to be transferred via TXD must be placed in SBUF. Similarly, SBUF holds the data when it receives also. Is it right? I have shown you. It can be accessed like any other register of 8051. Look here. There is one assembly language instruction which is saying that move SBUF hash D. When we are saying D, it is the ASCII D, and ASCII in ASCII D means 44H. So what we are moving to this S buffer? 44H. What do you mean by 4? 1 0 0 1 0 0. I just talked about 6-bit. Actually, it is 0 1 0 0 0 1 0 0. Is it right? That will be available in the 8 bits of S buffer. Okay. Then further, what this instruction is saying? SBUF A. Copy accumulator. What is there in the accumulator? Copy it on SBUF. What I am trying to tell from here is SBUF is the normal register, special function register, but normally you can use it in the program. Okay, it is the register of what? 8051. Any other register of 8051 which can be used in the program like this, along with the accumulator, directly putting the value, transferring it value to A, taking the value from the A, that is accumulator. Okay, that is how SBUF is there. The moment a byte is written into SBUF, it is framed with start and stop bit. I told you. Obviously, it has to be framed when you are sending it outside, right? Without framing, the receiver will not understand what it is receiving. Similarly, when the bits are received, again it has to be deframed. You have to take out those start and stop bit, else what will happen? Microcontroller internally, it will confuse those bits with the data bit. We don't want it. We have to remove it and then to send the data down. Okay. Now, for this serial communication, there is one more SFR which is SCON, Serial Control Register. For controlling this serial communication, it is there. Okay, look what is there in this SCON: SM0, SM1, SM2, REN, TB8, RB8, TI, and RI. Okay, so obviously these are the mode specifier in which mode the communication is happening. That is getting specified here. Okay, so SM0, SM1, and SM, these two, these are mode specifier. Means, what do you understand? How many mode we can control with help of this? As there are 2 bit, 2 to the power 2, means 4. 4 modes can be there. Is it right? These 2 bit can be 0, 0, 0, 1, 1, 0, and 1, 1. So 4 mode can be there. We can think of 4 mode here. What about this SM2? Used for multi-processor communication. Okay, when we are communicating with multiprocessor, that can happen here. What about this REN? It is receive enable. We are serially receiving the data, but enabling to receive the data, so that receive enable. By software, we can make it enable or we can make it disable. When we don't want to use, it has to be disable. That control has to be disable. When we start, we want to receive it, at that time we have to enable. What about TB8? Transmit bit 8. Okay. And what about RB8? It is transmit bit 8. This 8th bit of either transmission or reception will be coming here. Okay. Then, and try to understand that is of use, because understanding your data is most important. So if you have to match with those bits, received bit, is it the same one which we are decoding there? If it is yes, means our data frame is okay. That's why these two bits are there. T1, it is the transmit interrupt flag, and R1, sorry, it is TI and RI, not one, receive interrupt flag. Okay, these are the transmit interrupt flag and receive interrupt flag. Set by hardware, clear by software. We can set it, and the software, once that subroutine is run, it will be clear. Again, we can set it, and the routine, when completed, it will be cleared, right? So that way it has to be utilized in program. And as I told you, how many modes? SM0, SM1, 4 modes are there. Mode 0, 1, 2, and 3. And what different operations can happen? In mode 0, that serial communication is acting like a shift register. As it is simple shift register, it is happening, that shifting is happening with the frequency extal by 12. That is the baud rate by which, that is the frequency with which changing is happening. Whereas in 01, that is mode 1, it becomes 8-bit UART. Okay, how many bits? 8 bit. Means your frame is of 8 bit, accompanied by start bit and stop bit. Okay, variable who is helping to give the baud rate? Timer 1 is helping to give the baud rate. 10, when it is 10, it is mode 2 and it is your 9-bit UART. Okay, it is fixed. What about the baud rate? Extal by 32 or extal by 64. This can be the baud rate available there. Then in case of 1, it is mode 3. It is again 9-bit UART, which is transmit rate is variable and controlled by timer 1. That way the mode is there. As and when we go for the programming, utilize these things, it will be of more use. Okay. At first we have to understand it, and then it is required that we are utilizing it. Okay. They are making the program, what you can say, more powerful. So every mode they are talking about. So very shortly I'll go through this mode and I'll stop here. From next time we'll start with the next microcontroller, mode 0. What was mode 0? The shift register. Look here. This is 8051. It's pin TXD, it's pin RXD. TXD is sending the data. It is acting like the clock. RXD is happening. Okay, and the data is getting shifted, coming in, or shifted and available here. So it is the shift register which is happening to be there. Now why to use this type of thing? It is for port expansion. We are getting, with help of this one serial pin, look how many pins we are getting. 1, 2, 3, 4, 5, 6, 7, 8. More 8 pins. Port expansion is happening here. Only this thing I'll talk about. And that's why, look, it is running at machine cycle 1 by 12. What is the rate with which it is working? 1 by 12. By the same rate, machine cycle it is running. Okay, that's why it is just the port expansion which is happening. In mode 1, what is happening? 10 bit are transmitted through TXD or received through RXD. What do you mean by 10 bits? 8 bit of data, 1 stop bit, 1 start bit. That way 10 bits are there. Okay, when we receive this bit, the stop bit goes into RB8. Who's RB8? That S control register. RB8. There it will go. The baud rate means it is going there means what? We are understanding that one frame is completed. The baud rate is determined by timer 1 overflow flag. Obviously. Okay. Timer 1 clock is 1 by 32 machine cycle. That is 1 by 12 extra. Okay. Time 2 timer 1 by 32 is going, and it will divide it further to give the required baud rate. Timer clock can be programmed as 1 by 16th of machine cycle. Transmission is initiated by any instruction that uses SBUF as an destination register. In total, uh, SBuffer, SCON, we are utilizing to program these things, as well as we are utilizing the timer, and timer interrupt has been used here. So that is how mode 1 operation is happening. Similarly, the mode 2 is going for 11 bit of transmission, means in this case we have a start bit, 8 data bit, a programmable 9th bit, and then the stop bit. That way it is of what? 11 bit in total, and further everything is almost similar. Okay. Mode 3, it is same as mode 2 but may have variable baud rate generated by timer 1. So depend what is our requirement. Depending on that, we will be selecting the mode. Do we want the programmable 9th bit? In that case, we will be going for mode 2. Do we want the variable baud rate? We have to go for mode 3. Okay, and so on. So depending on our requirement, we can think of the mode to be used. And the last thing, there is one more important SFR, that is SMOD. Okay, and not complete SFR. This SMOD is 1 bit of PCON register. There is one register called as PCON, and its MSB is SMOD. Okay, bit 7 of PCON register. If SMOD equals to 1, what will happen? Baud rate will get doubled. PCON is not bit addressable. We have to address it completely. So SMOD, if SMOD is 1, baud rate will get doubled. But we have to address it completely. So how to set SMOD? Move a PCON, set accumulator 7. Okay, anyway, just try to understand that we have to set the complete values here in the SMOD, and out of it, SMOD, this high last bit has to be 1 to double the baud rate. Okay. So programming of 8051 to transfer data serially, just one by one. We'll try to go through it and we'll stop here. So load your TMOD register with 20H. Why? Indicating use of timer 1 in mode 2. What is TMOD? Here we are deciding which timer we are using, what mode we are using. So 20H will be loaded to it. And by loading 20H, it is giving us timer 1 in mode 2. What is mode 2? It is 8-bit auto reload mode. And why? We need it for setting the baud rate. Clear? So that is the first thing we have to do in our program. Next thing, load TH1. Now, depending on the requirement of baud rate, you are putting the value in TH1. I have just shown you, if it is -3, what has to be there? For baud rate of 9600, what has to be there? For some other baud rate, what has to be there? So accordingly, we have to set what? TH1. And only TH1, only this bit, because remaining 8 bit of that timer will be used for what? Auto reloading. Okay. So load TH1 with one value in table to set baud rate for serial data transmission. And what is our assumption of the frequency? This 11.0592 megahertz as the clock frequency of 8051 we are assuming, and based on that we are loading the value in the timer register. Then we have to load SCON register with 50H. Why 50H? This 50H means what? 0, 1, 0, 1, and then for this 0 again 40, indicating serial mode 1. Again we are selecting the mode. You can go for that SCON register, you can check it. When we put this value, what is happening? We will be indicating serial mode 1, where 8-bit data is framed with start and stop bit. Right? This is the next step to be done. Once this is done, set TR1 equals to 1 means we are starting the timer 1. Okay. TI is cleared with clear TI instruction. Then the character byte to be transferred is written in SBUF. Okay. Monitor TI flag. We will be monitoring the TI flag with this jump type of instruction to see character transfer is over or not. When the flag is set, it will be over. To transfer the next, again go to 5 and do the same thing. This will run almost in the loop, transferring all the data. That way the programming will happen in case of serial communication. Okay, you can try writing down the program. I have the program in assembly level language. I'll be just displaying one statement in front of you to write a program to transfer later y. Y means what? In ASCII, what is y? That you have to decode and that has to be transferred. It has to be transferred with baud rate 9600 baud rate continuously. Data has to be sent serially to which pin? Port pin 3.1, that is TXT, and baud rate is 9600. And for this baud rate TH1, what value has to be loaded? -3 has to be loaded. Now think of these all instructions and one by one they have to be done to get your program. Okay. Then also I'll be putting this assembly level program in front of you. Look, in assembly language, what is happening? In T mod, we are loading 20H means timer 1, mode 2. This is 8-bit auto reload. In TH1, what we are loading? -3. Okay, that we are loading. Why? To set the baud rate of 9600. SCON, what we are doing? 50H we are loading. Okay, and by loading 50H in SCON here, load 50H indicates serial communication in which mode? In 8-bit mode, that is mode 1. That's why 50H. Set B to TR1, start the timer. Loading is completed. Now we have to start transferring. That's why timer will start. Okay. Once the timer is start, what is happening? Move SBUF. What we are moving to SBuffer? Y. Transfer Y. But this transfer is happening serially. It is the ASCII code and it is shown by coded by 8-bit. It will be transferred one by one. Okay. Then here we are wait for transmission is over. This jump statement is waiting for transmission to be over, and for that it is checking the TI. It is checking TI flag. Okay, and once it is over, if it is not over, it is again and again jumping, right, and getting it completed. Why? Total 8-bit. So 8 times it will jump and get it completed. Then clear TI. TI will get clear, and then again the jumping on where again is happening. Sorry, here we are jumping back here. Okay, and in case of again we are jumping back here, jump back to repeat, and the repetition will happen. That way the program is going to run in assembly level language. You can think of few more program. So that way we have completed with the uh, serial communication of 8051. But I would like to request you people to write down the programs, take these statements, write down your program on your own so that you can understand the functionality. Once you understand these functionality, it is possible to easily understand the higher processors, controllers. Else it will be difficult for you people. Okay, so I'm stopping here for today. Any question? Yes. Acha, in that some slide. Acha, these are few more examples, nothing else. These are few more examples of serial data application. I can take it. No, no. I'm finishing with 8051. Okay, okay, okay. So the next is write a program to take data through port 0, 1, and 2. one after the other and transfer this data serially continuously. Okay, so write a program to take data in through port 0. From where we are taking the data? Port 0, 1 and 2. One after the other and transfer this data continuously, serially, continuously. That has to be done. So if we are thinking of this statement, look what is happening. Again, we are setting the tmod register. Okay, we are setting it to 20H. What we mean by 20H? 0010 and remaining all 0. So if you check the tmod register, you will find out that we are setting timer 1 in mode 2. That is 8-bit auto reload mode. And everything this is happening because we have to set the baud rate. Okay. Then, depending on the requirement of baud rate, what we are doing, we are loading the value in TH1. Okay. So we have to check with what baud rate to communicate with that computer or whatever is the machine there. So accordingly, we will be loading the value in TH1. Okay. Then, as it is 8051 microcontroller, the frequency we have to think of is 11.0592 megahertz. It is almost the similar part we talked about in the previous case. Then, load SCON. Okay, we have to load the value in SCON. Here, loading the value in SCON is for selecting the serial mode communication. Is it 9-bit communication? Is it 8-bit communication? What we are doing, that setting that is happening by setting the values in SCON. Okay, so presently we are setting it to be 58. So if you understand, if you try to understand, on almost same line everything is going. Where will be the change? The data transfer. There the part is changing. Okay, so loading of SCON is happening. Here TR1 equals to 1 means we are starting the timer. TI is cleared. Okay, with clear TI instruction. At first we are clearing TI. The character byte to be transferred is written in what? SBUF. And then we are monitoring the TI flag. Okay, whenever it is set, the character transfer is over. And then we are jumping back to the 5. That way the transfer is happening. Okay, so again this is the program in assembly level which is talking about the transfer for the statement which we use there. Okay. This one is about, that one was about transmitting the data. Here one program is talking about the received data serially. Okay, both the program we talked about the transferring of data. Just one shortly we'll go through this receiving of the data. So again we are loading tmod with 20H. I'll not explain it now. Load TH1 depending on the baud rate. Load SCON indicating the serial mode where 8-bit data is framed with start and stop bit. TR equals to 1. Start the timer. Now, instead of TI, what we are using here? RI is used here. RI is cleared with clear RI instruction and monitor the RI flag. Right? That will tell about what? Receiving the data. That is only the change happening between transmitting the data from the serial port and receiving the data from the serial port. And that way the things are happening. Okay, so even using the serial communication, you can think of typing on the monitor using the via your microcontroller. You can think of typing on the monitor of the computer. So that way, try to execute the serial communication at your level. Okay. Just I'll read the statement. If it is of use, then only we'll think of, else I'll stop here. Write a program to receive the data which has been sent in serial form and send it to port 0 in parallel form. Also save the RAM location 60H. So that type of statement has been given. You can think of doing it. If you people want the PPT, even I can share these PPTs to you. Okay. So I'll be stopping here. Yes, any question? Okay. May I stop sharing? May I end the meeting? Actually, 8051, whatever we were talking about is over. From next time, I'm starting with PIC microcontroller. Okay.